Hello all, welcome to Quantastic Academy. Welcome to Quanta series video number 4. Today in this video we are going to be solving a question from Irodov. This question is from conservation of energy, momentum and angular momentum. In the previous 3 videos we solved problems, and one of them was from Rustic and Halliday and 2 questions from JEE Mains. And today we are solving questions from IE Irodov. Similarly, we'll be dealing with questions from the other subjects. We'll be solving questions from electromagnetism, optics, and even dual nature of atoms, so on and so forth, from various resources. So without any further delay, let's get into today's question. It would be nice if you kindly subscribe and like the video, and please do share the video, and if you have anything to say you can share it in the comment section. That will help the channel to grow, and it will also motivate us to post a lot of videos. So without any further delay, let's get into the solution part of it. So a chain of mass m equals 0.8 kg and length 1.5 meters rests on a rough surface table so that one of its ends hangs over the edge. The chain starts sliding off the table all by itself, provided the overhanging part equals eta, which is equal to 1 by 3 of the chain length. What will be the total work performed by the frictional forces acting on the chain by the moment it slides completely off the table? Okay, it's a very good question. In fact, many students feel heavy looking at such chain related questions, but today let us solve this with ease. So the first thing is, let's consider a table and a chain which is on the table and some part of the chain is actually hanging. So let's assume that the length of the chain on the table to be x and the remaining hanging part is L minus x, since the net length of the chain is assumed to be L. Okay, and we have considered uniform mass density, which means uniform linear mass density, which means that mass per unit length is uniform, which is the same in all points of this chain. Now let's discuss the initial conditions. Initially the chain is at rest, which means that the frictional force or the limiting force actually is preventing the chain from falling down. So this overhanging part actually is responsible for the falling of the chain, and this limiting force actually prevents it. So the limiting force being in this direction and gravity acting downwards, this is pulling it down, this is restricting it from falling down. So at equilibrium I can safely say that the limiting force is actually equal, which means that the limiting force is actually equal to the weight of the hanging chain, right? So from here I can say that the limiting force is actually equal to lambda times L minus x into g, and it is given in the question that the overhanging part equals eta's value is 1 by 3 of the chain length, which means that I can say that L minus x is equal to eta times L. And from here I can also take another relation, L minus eta L equals x. So x equals so x equals L into 1 minus eta. So I have two relations now. I use the first relation, L minus x equals eta L, and I put it here. So I get FL equals lambda eta L and G, right? Now how is the limiting force, or the limiting friction given? It is a quite simple way to write or represent FL. We know that the coefficient of friction between the table and the chain is actually given by, either you can go for mu or even K. Some books tell that we can use k, sometimes it is given as mu. So let us assume that the coefficient of friction, the coefficient of friction is k, and this is between the surface or the table and the chain, right? So this is there. Now we know that FL equals eta times L, G and the lambda, right? But what is FL? FL is actually the limiting friction, which is actually given as K times lambda x into G, because lambda x y sorry because x is actually the length of the chain actually present on the table, which is lying on the table. So for all purposes I can say that FL is actually K times lambda times, this time instead of x we go for L. We found it initially, right? We found it by telling that L minus x equals eta L, and from there we computed for x, and this is what we get. Now we have two equations and we equate them. So LHS equal to RHS, right? And I cancel L, I cancel G lambda, I forgot a lambda over here. Yes, here it's present. Nice. Okay, so lambda and lambda gets cancelled. So from here I can therefore say that the coefficient of friction is actually given by this formula. Beautiful, right? Now we dissolve to the next part. We are actually asked to compute the work done due to frictional forces, right? Frictional force present, right? We know that work done is actually given as the negative integral of f dot dr, right? So here we apply the same concept and we write that the work done is actually equal to the negative integral of F, which is your frictional force. Your frictional force is actually given as lambda x into G, right? Times dx, and actually the chain has fallen down completely, which means that the upper limit is equal to 0. It is completely fallen in the sense that the chain is completely fallen to the ground, which means that it is 0. From where has it fallen? It has fallen from a height L times E1 minus eta. Okay. Looking at the diagram, we can compute it, and this is what we have. See, the first it was x, and this completely. So initially it is at initially x is the length of the chain which is present on the table, and finally it has fallen completely down to the ground. So I can write it like this, and once you compute this you get something like this: k lambda g x squared by 2, and when you apply the limits L into 1 minus eta to 0 and I compute this, I get k lambda g. So anything 0 is actually 0 squared is again 0. So this time we get 0 by 2 minus L squared into 1 minus eta squared, as simple as that. And now I can write for k. So k was actually found out to be something like this, right? Beautiful. Square and square gets cancelled out, and already we have a minus sign over here, so this minus and this minus gets cancelled out, and this can be further written as work done is equal to eta times 1 minus eta L. Am I right? L squared lambda G. L squared lambda L squared L squared lambda G. L squared lambda G by 2. Did I forget a 2 over here? Actually, I forgot a 2 over here. We have a 2 over here. Okay. Now it is all the same, which it's all done. So from here I can say that the work done is actually given as eta into 1 minus eta, and this can be written as L into L times lambda G by 2, and we can say that so here we have lambda L times G, so this quantity can be given as M, which is the mass of the net mass of the chain. So from here I can say that the work done is equal to eta times 1 minus eta L into M G. Sorry, I shouldn't be considering G. This lambda, actually lambda L is equal to M. M by L equal to lambda, right? So I have this G coming in, whole divided by 2, and we know the quantities in fact. So we have the mass of the chain, which is 0.8 kg, the length, so the mass is 0.8 kg, the length is actually 1.5 meters, and this eta was actually given as 1 by 3 times L, so 1 by 3. So when you compute this, you get something like 1 by 3 into 1.5, and when you cancel this out, you get something like a 0.5 again. So when you substitute it, you get something like this. This 0.5 into 1 minus 0.5 into 1.5 into 0.8 into 9.8 divided by 2, and it is a mere substitution. And further, when you calculate this, let me compute it using a calculator. So when you do this calculation, you get 1 minus 0.5 again gives you 0.5. These two, it is actually 0.25 times this and this, and approximately you get something like 1.3 joules. As simple as that. So this is it. So you have solved the work done, or you computed the work done due to the frictional forces acting on a chain that has completely fallen off a rough horizontal table, right? So this is it. Such a beautiful question from IE Irodov. Similarly, we'll be dealing with questions from electromagnetism and other subjects as well. Stay tuned for the upcoming future videos, and please do subscribe, like, share, so that the others would also get to know more about this, and this will indeed help the channel grow and will also help us share our knowledge with all of you. Let's meet in the next video. Thank you.